see. Hello, guys.
Good afternoon, teacher.
Good afternoon. Okay, so let's see. Let's see. Let's see if more of you guys join or not. Okay, we have 16. Let's just wait a few more seconds and we can start. Oh, okay, let's see. Let's just get it started. Okay. Okay, 17 of you. Let's see what happens. So the last time that we were together, we talked about Doppler imaging, right? And we finished actually talking about Doppler imaging. So let's get to talk about something else to wrap up, in general, these discussions on ultrasound and whatnot. Okay, so let me see. There's a lot to say about elastography. Actually, if one were to talk about these techniques like in actual depth, we would probably have to, spend, I would say at least, a month or something talking about this. But we're going to give a quick overview, just because I think that's, it's a relevant piece of technology that you can find in most, if not all, the I want to say all high-end scanners nowadays, actually for quite some time. Okay, so I think it's really important that you get to know a little bit about this. The basic idea of elastography in general is related to the knowledge that typically when you have diseased tissues, they get to be stiffer than the normal tissues. Okay, and this is a broad assessment. Like even when we talk about, for example, like cancer, we typically think or assume that cancerous tumors are stiffer than their benign counterparts. Or in general, if there is some tumor in your body, you can palpate it, right? Because you notice something different. For example, you can palpate your thyroid glands, or you can palpate the mammary glands. And actually, palpation is, one of the recommended self-evaluations for females, to check in case there is something abnormal. It will happen also after a certain age, when you have your yearly checkup. Simply because, it's some sort of a common sense thing, right? For prostate cancer, it would be the same thing eventually, So it's just, again, things to know and think about. So the idea is to do it non-invasively, right? If you can do this non-invasive palpation, which is the motto behind, in general, radiologic techniques, right? And that's what the field of elastography in general does. It relates to, I would say, in general, viscoelastic properties, and we'll get to talk about that in a little bit too. but just the elasticity in itself, right, is a property of a medium that enables it to change length, volume, or shape because you are actually applying a force, and that it can recover its original form upon removal of said force. Okay, so for example, if I have, you know, a sphere made of glass, I can shatter it, you know, but it won't reconstruct, you know, after I remove the force that shattered it, right? So that's not our idea of what elasticity is, right? And when you have an elastic medium, it would have to be a solid medium. A fluid medium wouldn't support elastic deformations because it just doesn't, right? Fluid medium means that the relation among the different particles is they can basically, you know, they are free to move. They induce changes again because of the changes in local density, you know, that will force them to re-expand or recompress. But in general, you know, that's our idea of what a fluid is, right? I mean, I just push something and it just gets pushed, right? As opposed to, I don't know, I have a muscle, and if I do something like this, I don't expect, you know, the muscle to just like push, go away for miles and miles, right? I mean, it would wiggle a little bit, but it will stay in place because it's solid, right? So the whole idea of elasticity is linked to solid media. And you cannot just apply any type of, you know, force to a solid medium and assume that it's going to behave elastically. I mean, you can, again, you know, a piece of glass would be a solid medium, but you can shatter it, and that's not an elastic distortion, right? So again, many things that you probably have studied, you know, in high school and a little bit in, you know, your college years too, you know, the idea and the notion of what I'm talking about. Again, the whole reason why this becomes important for clinical practice is because in general, when you have pathologies, you associate it with an increased stiffness, right? So for example, in here you have, you know, curves of the stress strain, right? So you have the strain horizontally and the stress vertically. Do you guys know what stress and what strain are, by the way? I mean, you should know, I'm pretty sure, but I mean, does anybody care to elaborate on a definition of what strain is and what stress is?
Stress will be the force experienced by the object,
Okay.
and the strain is the change in the object, the change in volume, I guess, or shape.
Right, exactly. The strain gives you the formation. The stress tells you, you know, the pressure actually that's applied, you know, to the medium to induce that deformation, right? So when you have the strain stress curves, like typically, for example, if you have, let's say that you have a spring, right? Which is a classic thing. Then what would you expect the stress strain curve of a perfect spring be equal to? What should it be?
Proportional?
It should, right, it should be a straight line, right? And the slope of that line should be that K constant, right? The that whenever you have, you know, a spring mass system, you say it, you know, here's your constant K, and that constant K would be that slope. But of course, you know that in practice, again, if you keep pulling the spring, eventually you're going to break it, you know, like if you compress it too much and things like those. So in general, those curves are going to have different regimes, right? So they're not going to be a perfect line. And there are many other things that, you know, deviate away from that perfect, you know, here's one, you know, straight line thingy. But here, for example, you can see that you have, you know, normal fat and normal glandular tissues, right? Which are those two curves that are, you know, down the bottom. And then you get to see the stress strain curves for ductal carcinoma, for infiltrating ductal carcinoma, right? And also for benign fibrotic lesions even, right? And you get to see that those are actually ramping up at a higher slope than normal tissues, right? So if you were to look at that, spring constant, right? If you were to look at the slope of those curves, the malignant tissues would have a higher slope, right? So that's basically the idea, behind all of this. And this is just, placing common sense again, related to palpation. Say whatever, however you want to say it. It's just, this is stiffer, right? That's I guess in the end the bottom line. And these are some of the things that we have been talking about, right? Like in general, you have a bulk modulus, right? And the bulk modulus would have to be basically that, right? You have your differential of pressure, and you have your differential of volume, right? And it's the one that relates the two of them. You have a Young's modulus, which is the one that is related specifically with deformations of the longitudinal type, right? You remember we talked about longitudinal and shear, right? And this is where everything kind of starts coming together, I guess, in a more formal way, which I also thought that was another reason why it would be advantageous to at least, briefly discuss over some of these concepts. The shear modulus, right? It's you're applying that basically the shearing, right? Shearing means doing something like this. And you're deforming, you're actually deforming the tissue or the material, right? In a shearing shape. So the shape is actually changing in that way, right? It's distorting, unlike the case of the compressional one, in which you're not really like distorting anything. You're making it shorter or longer, but you're not distorting the shape, which is mainly, again, the difference in between the shearing and the compression and the compressing. So again, you're gonna have Hooke's law, right? It says that the force is proportional to the distance a load applies to a spring, right? So I have my spring and I start to pull it and I pull it and I pull it and I pull it and I pull it more, right? And I pull it at certain distance X. And there is going to be a force made by the spring that's opposing, me pulling the spring, and it's going to be higher the larger the deformation is. And it's basically going to oppose to it. It's directly proportional to it, right? So you can actually go, along the same lines when you have Hooke's law for compression extension, right? Which is going to tell you that basically the stress sigma, right? So you have your pressure, which is force divided by area. So your stresses, because when we're talking about solid media, we talk about stresses. We don't talk about pressures. Actually, propagation in solid media is in general more complicated, right? In fluid media, it's just what it is. It's relatively simple. In solid media, it's complicated because something that you apply in one direction produces, in general, those things that we're talking about, changes in density, velocities and stuff like that, in every possible direction, right? Again, understandable, right? They compress something, it's a solid piece of medium, it compresses like this, but it also expands on the sides or it shears a bit. So depending on how I apply the forces, a whole bunch of things can happen to the medium. So what you have are stresses, right? It's the same idea that you have force divided by surface area, but you have stresses. And this, happen in some directions, and they're going to induce effects in every other possible direction. Remember, in a way that's different than what we assume, in the case of fluid media, we have a force, right? And the forces are in some direction and the effect happens in that direction too. So again, it's the usual thing, right? You have your stress sigma, which is going to be equal to, the deformation or the strain, right? Multiplied by your modulus compression, right? Which is what we define here, the Young's modulus, right? So basically, right, these are the things that we already know, right? Which again is that sigma, or stresses or forces, normalized forces, are equal to the strains multiplied by the Young's modulus. We know that forces are also equal to mass times acceleration, right? We kind of know those kind of things. So we can actually march, through basic ideas on how to put together these equations in a way similar to what we did for, the propagation in fluids. And we can actually come to an expression that tells us that, second derivative with respect of x of the particle velocity is going to be equal to 1 over sound speed to the squared, and the second derivative with respect of time of that velocity, and that would be our wave equation with a longitudinal wave speed that's equal to square root of E, right? The Young's modulus divided by rho, which is the density. And that is something that, came up in one of the questions that we had, I think, during the office hours, right? So I thought it would be nice to have it in there too, how you actually relate these kind of things, to one another. So anyway, remember that would be, for compressions, but then when you have shear stresses, right? Then we have a forces parallel to the cross section. And now what we have is a shear modulus, right? Which is G or U, right? Which is a material parameter that relates to elasticity due to shearing, right? Again, you can have elasticity due to compression. You can have it due to shearing too. And by the way, these are things that, I'm assuming a lot of the things I'm talking about right now, you already know them, right? But shear and Young's moduli are related through a quantity that's called the Poisson's ratio, right? Which is kind of funny because Poisson is fish in French. But anyway, so the ratio is going to be equal to this, right? Mu is equal to E divided by 2 times 1 plus Poisson's ratio. And that's a pretty fairly well-known expression. If you didn't know it, then it's there, right? But it's basically telling you that, again, all those quantities are meant to be related. And hopefully that's the case, right? Because again, if you're applying stresses and you're deforming a medium, you will have to imagine, right, that, a medium could not, like in theory, support, a wildly different elastic behavior. Like, I allow a lot of compression expansion and, the shearing, something that there has to be a number that keeps them together and balances them out. There can be wildly different. Actually, the behavior of the stresses can be highly anisotropic, right? And there's always a quantity that relates them, and that would be, again, Poisson's ratio, right? And in general, when you have the propagation of waves in solids, you have your longitudinal wave, which is, it has a speed of square root of E divided by rho, your shear wave, which has a speed of square root of mu divided by rho. And this is, of course, assuming there's an isotropic material, right?
Teacher,
yes.
Sorry, when we were talking about the a previous slides back, can you go one more? There. Is it only applied to rods or
in this particular case, and just to simplify the discussion, we're basically assuming that this is derived for a rod, but you had a very, very elegant derivation of the wave equation anyway, right? For in general fluid media, and it actually carries on. This is just to show you guys that it carries over, not to overcomplicate things actually.
Okay.
Sure. So there's the idea of the bulk modulus again, which is the resistance of the material to a uniform compression, right? And there's a compressibility, which is measuring, relative volume change in response to a pressure change, which is 1 over the bulk modulus, right? So when you have propagation in fluids, you have your longitudinal wave speed, but you don't have shear propagation because fluids cannot support shear stresses, right? And these are some typical parameters in tissues. I mean, you're going to probably find some more different numbers. And we know that, in general, we try to compile these tables over and over, and we go to different sources and we come up with somewhat different numbers, right? But what you can see in here, right, are many, many things. Like, for example, you have, a healthy liver and you have a fibrotic liver. And if you actually go to the bulk modulus, for example, right, which would be equivalent to figuring out what the compressibility would be equal to. Actually, the range of the bulk modulus is like everything is kind of the same for everything, right? Which is one reason why, imaging of the bulk modulus is not particularly exciting, for ultrasonic tissue characterization. But when you actually go to the shear modulus, for example, right, the healthy liver has a shear modulus of 0.3 to 4, whereas a fibrotic liver has a shear modulus of 10 to 100. So when you think about it, if you were to image the bulk modulus, there's little contrast to be had, but when you image the shear modulus, there's a lot of contrast to be had. So you're probably better off, determining that parameter, the shear modulus that is, rather than the bulk modulus. You will observe also, something really interesting, I guess, in a way, which is that for most of this, the shear modulus and the Young's modulus are kind of related to one another, right? So what seems to be the relationship between the two? From a quick observation.
There's a factor of 3.
Yeah, there's a factor of 3. Right, and that happens in this particular case because we have a nearly fluid-like behavior in the tissues, meaning that Poisson's ratio is probably very close, but not exactly equal to a value of 0.5. And that's going to make your relationship, or a classic relationship that you would find between the shear and the Young's modulus, being given by a factor of 3. Again, that's something that very commonly, researchers would do, like if they want to figure out, for example, they estimate, the shear wave speed, for example, and from there they get the shear modulus. But then when they want to figure out what the Young's modulus would be, then they extrapolate it with, that particular factor of 3. It's very, very common in the elastography literature, again, because of, the relationship that would be given by the value of Poisson's ratio that you would expect from, nearly incompressible solids. There are direct measurements of elasticity, because for everything you have to have, some sort of a ground truth, right? And these are load displacement tests. And I remember my best friend in college, she was from Cornell University and she works for Kraft right now. I think she was a food science major, would have this type of of equipment in her laboratory. And she would, use this to measure even tensile strengths from human hair and stuff like that. For research purposes. But you can see in this type of curves, right, some of the things that we're talking about, these are not straight lines or anything. They have different slopes, for different values of the strain. So you have to, pretty much you can use this for an accurate determination of the elastic properties of materials. But then you get to the beautiful field of imaging, right? And here's where it gets to be more interesting. So for imaging, there are really many, many different ways to construct images of elasticity. Again, there is no way of making justice to everything into one lecture, but here we are, right? So we're gonna try. And the only reason why I'm going to present some of these things is because I just want to give you an overview of things, so you get to be familiar, with the technology, but also so you can relate, concepts back to the things that we have been studying so far. Spoiler alert, right? You have been learning things that are actually pretty basic. And I know that for some of you that may sound discouraging, because it's like crap, because that actually seems kind of tough. And it is, there's a lot of math, there's a lot of physics involved, so many concepts to, keep together. But when you go down to, what you actually find in scanners, there's a huge gap in there. And the idea behind this course is not to just, like kill you with details about what's really in scanners nowadays, but to give you a solid overview of the basics, so you can extrapolate things, for after. So you have static, so you have different types of excitation, which can be static, quasi-static, and dynamic. And you have different ways of measuring the elastic behavior to construct the images. You can do it with ultrasound, you can do it with MRI, you can do it with CT, you can do it with OCT, right? Which optic coherence tomography too. So you have optical coherence elastography, for example. So the basic idea of elastography, right, to create an image of a medium is that you apply a known static force, right? And we're talking probably, you know, when we talk about this idea of strain imaging, which was one of the first algorithms that was proposed in the literature for creating elastographic images. So you apply a known static force, right? And you actually measure how the medium is deforming. And you do that by basically, you know, you have, you know, your force, which in practice, it actually would be the sonographer has a transducer and starts, you know, like applying a very slow control force, like basically compressing with the transducer itself. Okay, that's how these things actually got to work, you know, in the very early days of elastography, mind you. So when you actually do that, you're going to see that, you know, like again, because the tissue is compressing, then you're going to look at, you know, the underlying echographic images, and you're going to see that they're compressing too. So what you can actually do is for every point in the image, you can figure out how much the tissue displaced, right? And with that, you can actually compute the strain, right? And with knowledge of both of them, you can actually create images of, you know, the Young's modulus. And, you know, just to give an idea, imagining here in this cartoon, right? What you have is, so you have one medium and another medium over here, right? One is hard, the other one is soft. You apply a force, right? And you're seeing that, or you're observing that this one compressed a lot, right? Both media actually had the same initial length, right? The blue one compressed a lot. The red one compressed very, very little. So you know that, you know, the red medium is stiffer than the blue medium, right? So if you were to create an image, right? So maybe you have your ultrasonic image and you get to see the interface, and the interface is here. And then in the second image, you know, your interface, because you're compressing, your interface moved all the way to here, right? So you know that, I mean, you apply a certain amount of force, the actual location of this interface shifted, you know, by this much, and the other one, you know, shifted only by a tiny much. You know, it's like from here to here, dimensions reduced almost nothing. From here to here, they reduced a lot. And you know that you have a certain distance, right? And you have the new distance, you know, the compression, you can divide by the original length, and you can have the strains, and you apply the same force, and so on and so forth. And you can figure out roughly what is the relative stiffness of one medium compared to the other. But when you really think about it, this would have practical limitations if we were to, for example, look at the boundaries in between the two, right? Because you're not necessarily going to have, you know, it would involve tracking boundaries and things like those, and that's not the way that you do it. In practice, what you actually do is you track the changes at every depth. You don't go for, you know, the interface and say, well, the first medium compressed this much. Pixel by pixel in the image, you track how much things moved. And the way that you do it is by looking at, you know, you have in your first acquisition, right, pre-compression, you have some data. In the second one, you have, you know, another set of data, and you want to figure out how much every single point, you know, of data in your radio frequency signal moved because you compressed things. Does that remind you of anything that we have studied so far? Does that remind you of anything? Come on, guys, make me a happy guy.
Maybe you could restate it.
Say it again.
Yeah, but in other words.
Oh, sorry, I don't think I fully understood what you said. So it reminds you of what you said?
If you could like restate it with other words.
Sure. Basically, what we're doing is we are collecting one image, right? And we're going to look at the data that we're obtaining with the transducer. And then we're going to compress with the transducer and we're going to obtain a second set of data. And what we want is to compare these two data lines, right? These two lines of data to observe how much each point of data shifted, you know, in the first acquisition compared to its position in the second one.
Oh, then it is like a size algorithm.
It's exactly like Doppler.
Yeah.
Correct. There is one professor in Columbia University. Her name is Elisa Conofago. Maybe one day I got to invite her to give a lecture in here. And she's one of the pioneers in this kind of things, right? And in elastography. She's actually relatively young. She's a super nice girl. But Elisa actually, you know, was the one that proposed the algorithms that were the basis for the original compression elastography in Siemens scanners. And I like the title of the article is something like, it's actually that, it's basically speckle tracking. That's the name that it receives, right? It's tracking of the speckle or the granulation in the ultrasound based on radio frequency data, you know, and she envisioned it for applications both in Doppler and in elastography. Because in the end, it really is the same thing. You're trying to track motion, whether it is because the tissue is moving or because you're actually compressing the tissue, but it's kind of the same thing. Okay, so for me, that's kind of interesting again, because it just gives you an intuition or an idea of, okay, so I mean, I may not know exactly how to, you know, frame that problem, but I know roughly what is, you know, the mathematics that goes behind solving it, because I have a rough idea of the options I have to be tracking, you know, motion with ultrasound data, right? So it's kind of the same thing here. Like you have it pre-compression and then you compress it, right? And what's going to happen because you're compressing it, you know, some portions of the RF data are going to, you know, like appear sooner, others are going to appear later, and there are going to be small shifts that you have to track. And that's kind of the thing, right? They have to be small shifts. Because if you were to compress, for example, if you apply too much force, then you know that what happens, because we're actually talking about almost fluid-like, but really solid media, right? If you compress it, like we saw in previous slides, it's not only that you're going to apply a perfect elastic compression or expansion, but you're going to have a bulk deformation and you're going to move things to the side, right? And that's going to give you decorrelation, which is the same problem that you have in Doppler. You have log flow, you know, and you have a partial portion, right, of the vessel that you're looking at, and there are some red blood cells. Then time passes by, you have a partially changed, you know, group of red blood cells are going to give you a speckle pattern that is similar but not quite the same. So here's the same thing, because you're compressing and things are moving to the sides. Then the particles that generate the speckle are not exactly the same. They're similar, but not quite the same, which gives you also decorrelation in the data, right? So you have to, if you apply a lot of force, you decorrelate a lot, which is very similar to doing your Doppler imaging with pulsing very slowly, right? I mean, just wait here and then you wait for a really long time. Chances are you missed it. You know, your signal is highly decorrelated. With compression elastography, the same thing, but it's kind of the opposite. You know, you're trying to, you know, push things so you get to see more of a deformation, and eventually you only make things worse. Okay, just some things to keep in mind. So again, tracking using RF signals are better in the axial direction rather than all the other directions around. Boundary conditions give you problems too, because there's people that actually from static elastography try to create quantitative images. That's quite challenging, okay? But again, just moving around, you know, you get to see things like in here, for example, you see images in a phantom. These things over here, these are the phantoms that, you know, people in elastography would, you know, completely freak out about, right? They love these phantoms since I was a little kid, because I mean, you get to see that, well, if you look at the beam or the image, you see no difference whatsoever, right? But then you apply the elastography algorithm, and then you see clearly, you see a dark inclusion in an otherwise white background. So this is perfect, right? And that's not always going to be the case, of course, but I mean, this is a very practical reminder, you know, from the community that different sources of contrast in medical imaging are very advantageous. Because with some modalities, you get to see a lot of changes. With some modalities, you get to see no changes at all, right? For example, here you have, you know, lymph node imaging, you know, with a metastasis. Remember that lymph nodes are part of your lymphatic system, right? That's like the sewer of your body, if you want to call it that way. That's kind of disgusting. But remember that every time you have cancer, cancerous cells develop metastasis, which is they migrate to different portions of the body. If any of you ever had, you know, a friend or a relative with, you know, fighting cancer, you know that that's where it gets tough. Because once the person develops a metastasis, there is no going back. Okay. The cancer is already, you know, roaming around freely in the body. And there are two mechanisms for metastasis to develop, which is via the vascular system. And the ones that's like way worse than that is via the lymphatic system. Okay, so it's very important to actually monitor the lymphatic system too, and looking for things like sentinel lymph nodes and other things that maybe you have talked about and discussed in some of your other lectures in other courses. So we're not going to focus exactly on that, but it's very important to look into that. On the elastography, for example, in here, it's basically showing you that, you know, you can actually observe, you know, certain features in the elastograms that would, you know, help you identify a metastasis in the lymph nodes. This again would be breast imaging, right? You can actually see it from the images themselves, right? And hopefully, you know, you would imagine that that in this case, right, there is a lesion that's relatively round and well behaved. So this lesion over here would probably, you know, be considered to be a benign lesion. In here, you have, you know, speculated things, a more distorted pattern. So it would probably be, you know, if a sonographist actually were to look into that, it would be diagnosed as a malignant one. And in this case, figure B is an invasive ductal carcinoma, which is one of the most aggressive types of, you know, breast cancers that you can have. The first one is a fibroadenoma, which is one of the most common benign lesions that you can find in the breast that won't have an anechoic pattern. Like an anechoic pattern would be something like a fluid cyst. That's not cancerous at all. That's not a concern for anybody, right? But when you see things that have an hypoechoic texture, it can be cancer, it cannot be cancer. From the benign lesions with a hypoechoic texture, fibroadenomas are by far the most common ones. But in this case, you can clearly observe, you know, that there are differences. Again, here, most of the strain images are showing a shade of green. In here, they're showing a shade of blue, right? Which means that this is actually stiffer, because it's going towards, you know, the blue in here is coded as hard. And something very similar would happen in the images on the right, and you can explore them at leisure, you know, in your spare time. But this is, you know, roughly giving you an idea of what to expect, right? When looking at elastographic images, there are several things, you know, to talk about. And again, for example, you can argue, but here, you know, I see something reddish. You know, in here, I also see something bluish. So you don't like use it like elastography alone, you know, and you look at it and it's like, if something blue shows up, basically, you know, you have your echographic image, you know the lesion that you're going after. So if you know that there is a lesion and you focus only in that region, is that detection or is that diagnosis? Come on, guys, make me a happy guy. That's diagnosis. Thank you. So if you're going to grab anything from our, I think it was our first lecture, right? And you can see here that I'm just doing that all like kind of tricky thing where I refer you back to the previous lectures, right? So you can just humor me and make me a happy guy knowing that you guys were paying attention. There is a difference between diagnosis and detection, right? I mean, look at that image over there. You wouldn't be using this, you know, for detection of cancer in the sense that, you know, if something blue shows up, or if something, you know, like then it's likely cancer, because then it would be that would be unusual, right? But you can use it for diagnosis. You know, there's a lesion. The lesion is here. Just focus on that, you know, and see how, you know, relative values of the Young's modulus are changing compared to the background. So that would be compression. You have transient elastography. Transient elastography is actually very related to something because it's probably its most successful implementation would have to be the technology called as FibroScan. And you can look it up, you can Google it, which is not for imaging, but it's an extremely handy device that uses the same principles as elastography to actually determine stiffness in the liver. So you can actually non-invasively determine the degree of fibrosis. That's where the name comes from. So you don't even need an ultrasound scanner or an MR machine. So it's kind of neat. That's why clinicians love it, you know. So these things we kind of talked about before, like why the shear waves, and you know, and actually it's because of the increased contrast. So I'm just going to, you know, move ahead. These are just some things I put together. I think everything in there is important for you guys to read, but you know, in the sake of time, let's just move forward to other things. So actually, you know, in the transient elastography, you have low frequency transient vibrations, right? Which is different than, for example, something like sonoelastography or chronic wave elastography, where you have low frequency, but it's continuous vibrations. And here would be a transient one that's going to generate displacements in tissues. It's going to be low frequencies because you want to look at the thing go, and then you're going to detect them using pulse echo ultrasound. Okay. And this, for example, would be actually sonoelastography, right? Which is one of the things is vibrational elastography. Right, it's sort of a similar idea, just that instead of sending just a transient, you send a continuous. Okay, you send a continuous vibration, and in looking at the continuous vibrations, that it's actually very neat because what it does is it applies a technique that's also described in your material, which is power Doppler. Like if you actually power Doppler, what you get with applying that continuous vibration, right? I mean, you're applying continuous vibration that's propagating in the tissues, and of course you're going to have stiffer regions. And when that vibration gets there, you know, things are going to move just a little, right? And when you have media that is more softer, that's going to move a lot. So if you're actually receiving the signal and you're measuring not the speed at which the things are moving, because you kind of know it, but you look at the magnitude of how much they're moving, then you can actually determine which tissues are stiffer and which tissues are softer. And that is something that you do, again, look it up in your material with a method called power Doppler, which power Doppler, the only thing that it does is, which is kind of neat, you grab your data, you apply wall filters, so you eliminate the things that are slowly moving, you only keep the parts that are moving, and you integrate the signal, or you figure out what's the magnitude of the signal, right? Or the energy in the signal. Because if you actually do that, right, if you look at the traces in slow time domain, but you integrate overall, you don't look at the shape, you don't try to figure out how much things are moving, you're just trying to quantify how many, like how much movement you have, right? Then you have parts that are very bright, means that they're moving, that basically you have a lot of things that are moving. Parts that are shown as dark means that things are moving. It doesn't matter if fast or slow, right? But there's only a little bit that's moving. Here it's using that same idea, but it's with the opposite. It's with the opposite effect, actually, right? Because you're inducing the movement. So it's basically a matter of seeing in which parts you have the strongest movement versus, you know, the weaker one, which actually is related again to how stiff the medium would be. So again, this is another example of how, you know, even though it's a different technology, the same principles, the same algorithms apply, you know, and they're used in a different way, in this case, to construct elastograms rather than power Doppler images. Let's keep ahead. So there's magnetic resonance elastography, which is very interesting, right? So you're basically applying low frequency vibrations, and these are imaged with an MR device. So just in there, you know that the technique is going to be like super slow, right? But it's very, very interesting, actually, in the sense that, for example, in the Mayo Clinic, this was a technology that would have replaced or did replace the use of liver biopsies for staging of fibrosis. So this was a very monumental discovery, you know, MRE, which again is mainly used for the liver, right? And these are, you know, example of images of what that would look like And again, the person, you know, the stiffer the liver, because the higher the degree of fibrosis, you know, then, you know, the higher the value for the modulus that you're going to be imaging, right? And again, it gives you, like in here, for example, you have an image, and really compare the two. I mean, I know that you can say, well, I mean, yeah, sure, it looks like there is something different in there. Yeah, sure, it kind of does, right? But for the untrained eye, you can also argue that, you know, kind of, it looks like it's kind of brighter, you know, in the top, but I really cannot see much more than that. But if you look at the elastograms in here, it's day and night, right? So that thing that, you know, engineers would love to do with their phantoms, you know, it's something that's not completely removed, you know, from reality. And there is the issue of, okay, so for this, what we have, you know, in these types of elastographies, again, we have a drum and we, you know, make the person vibrate, or you have a driver that's propagating a slowly moving thing. But the one that you're probably more commonly going to find in the literature is the one, the elastography that uses acoustic radiation force. Radiation force is something very phenomenal. It means that when you're propagating ultrasound, ultrasound will also apply a force as it's moving, right? As it's propagating. And the force actually, and just skipping things like crazy, the force is actually going to be proportional to alpha, which is the attenuation coefficient, Z naught, which is the sound speed, and then the intensity of the ultrasound. So you can actually control it, right? So you can target or design ultrasound pulses that are of higher intensity than you commonly would use for imaging, and those you use them to generate a push. Of course, it's a micrometer, you know, type push in the tissues that then you're going to dynamically track with an ultrasound imaging system, right? And that's basically what you do, right? I mean, you generate a radiation force pulse in the vertical direction, and that's going to generate a shear stress traveling to the sides. And if you keep tracking, you know, with ultrasound operating in just conventional pulse echo mode, then you get to create elastographic images that will, and I'm going to skip ahead a lot, that would look like, for example, something like this. This would be, you know, for carotid imaging. And in this case, it would be for hepatic imaging, right? And you can actually do all those kind of things. And again, this is without the added need of applying an external vibration, which in practice would limit a lot of these applications. Everything is done just with the ultrasound scanner. The scanner applies the motion by using acoustic radiation force, and it tracks the displacements that you need to construct the elastograms by using just conventional ultrasonic imaging methods. So this was a brief overview, again, of elastography. You know, we can talk about it in more detail if you want in our office hours in the dive in those are tomorrow. But right now we have our guest speaker waiting for us in another Zoom session. So we're going to head out of here and we're going to go to, I mean, the link is in the Paideia system, right? For the second half of today's lecture. See you guys in a couple of minutes over there.
Okay, teacher. Thank you.
Bye.